Started. Okay, today our first speaker is Wenbin. He's going to talk about the supersymmetry indices of 3D negative for Chern-Simons matter theory.
Thank you very much. First, I would like to thank Satoshi and all the other organizers helping us organizing this wonderful workshop, and well, I was helped a lot by the organizer, so I would like to express my gratitude. And okay, I'm talking about so. Just a reminder of it seems that from Monday to Thursday, we are exploring this two-dimensional space of series, where one axis is dimension. So if I record it correctly, I guess right now, so 1, 2, 3, 4, 5, 6, they all appear, right? And in some background, of course, 11 and 10, happily appear, especially in the Yinan's talk and Java's talk yesterday, right? And the other direction, that the number of supersymmetry, of course, the number of supersymmetry has a lot of notations, but if I recall correctly, also, you see the number 1, 2, 3, 4, right? Occasionally, you see some weird number like 0.2 and then.
That's 2, right?
Yeah, that's you see that's whether this is a 2 or what, depends on the dimension, right?
That's true.
I mean that can vary, like
okay.
in some notation that may be like 16 or
That's
32
true.
or
That's
it's
true.
a weird number.
That's true.
And so it seems like so far we are exploring this two-dimensional lattice, and we also say like to better explore this two-dimensional lattice, we introduce or at least we encounter a lot of invariants or observables of the series. By the way, if you feel like my writing is too small, or have any questions, feel free to interrupt and stop me. As I did yesterday. Okay, so we have a lot of observables. I mean, some of them are useful, some of them are less useful. So it's some indices, right? I will start with less useful ones, and the partition function. And some more fancy ones like algebra of operators, but it may be local operators, line, surface defect, blah blah blah. Also, right? And some like even more fancy ones, TMF and so on. Okay. So that's a brief recap of what we learned so far. And okay, today I'm going to talk about some particular points in this lattice where d equal to 3 and n equal to 4. So happily, Yehao had already had an introduction for this kind of series yesterday. But I'm going to add something to his description yesterday. That is some Chern-Simons level. So I will add Chern-Simons terms to this 3D n equals to 4 series. And in particular, I would like to, even after the Chern-Simons action, I would like the series still preserve 3D n equals to 4. So I will explain how we actually get that later. And once we have some series with Chern-Simons interaction and the 3D n equals 4, I would like to study one of the not so useful observables according to Dupay, which is Susy index. So the reason I would like to study this observable is that I like to use that to study the modular space. Of of this series with Chern-Simons level, and also dualities. So we will see from the index computation that there are some interesting feature about this the modular spaces of the series once you have Chern-Simons term added. So one particular feature is usually without Chern-Simons action for the 3D n equals to 4 case. Okay. Usually we have for the 3D n equals 4 supersymmetry, we have the R symmetry is actually SO4, which is okay. Sorry. In my talk, I will not differentiate Lie algebra and Lie groups. So yeah. If you are more math inclined, please tolerate. Okay. So this is isomorphic to SU2H times SU2R. Sorry, SU2C. So its modular spaces are usually schematically have two branches. So one is called the Higgs branch, and the other one is a Coulomb branch. Okay. Of course, I mean this is the very rough picture. In general, you can have more complicated mixed branch. But the upshot is this SU2H acts on the Higgs branch, while this SU2C acts trivially on the Higgs branch. While the Coulomb branch was the other way around. Okay. So for the usual 3D n equals 4 series, usually this Higgs branch are not getting any quantum correction. So what you get from classical Higgs branch states after you consider quantum correction. However, the Coulomb branch got a lot of quantum correction. So that's why this to study the modular spaces of such series, this 3D mirror symmetry are very useful. So that is some you can always find the 3D series pairs which flow to the same fixed point, right? However, the Higgs branch of the series, let me write it this way. The Higgs branch of series 1 is isomorphic to the Coulomb branch of series 2. And the Coulomb branch of series 1 is the same as Higgs branch of series 2. Okay. And because for the 3D n equals 4 without Chern-Simons level, the Higgs branch can be obtained from the classical ones. So this mirror symmetry is a good way to understanding the both Higgs and Coulomb branch of the series. Right? So we just use when we try to compute the branch, we just use the vector picture. Okay. However, once you add, I will show later that once you add Chern-Simons term, the things change. And now the Higgs branch, because of the Chern-Simons level, the Higgs branch got quantum corrections, and it varies dramatically from the classical ones. Okay, so this is some feature from the Chern-Simons. Okay. So any questions so far? Okay, so of course I'm not considering randomly this series with Chern-Simons terms. So the particular construction for the Chern-Simons matter series that I'm interested in is I should also mention this is based on a work of my students Bohan Li and Dan Xie, and so this is the archive number. And just one day before our paper appeared on archive, that an Italian group led by Nopado, they also had a paper discussing related stuff. So yeah, so we should coordinate, but we didn't know that Nopado was also working on the same topic. So, okay, yeah, that's somehow that's a sign of like you know the how COVID really like stopped communication. Okay. So the theory that I'm talking about is starting from a 3D n equals 4 theory, right, with a flavor group. G1, G2 to GL. Okay. Then I couple each GL with n equals to 3 Chern-Simons term with a level k. So I couple this one with Chern-Simons level k1 and this one with Chern-Simons level k2 to the last one with Chern-Simons level k3. Okay. Well, for example, I start with I can start with a 3D n equals 4 bifundamental. So this is a 3D n equals 4 bifundamental hyper that transform as fundamental of un1 and anti-fundamental of un2. And one 3D n equals 4 hyper can decompose into chiral plus chiral anti-fundamental in the n equals 2 language. So for example, in this I started with this free series of bifundamental hyper and couple it with Chern-Simons term K1 and K2. But this is but the resulting theory is naturally 3D n equal to 3 Chern-Simons method. Then you will ask, okay, how come this can become 3D n equals to 4? So there is actually already following the work of Galto-Witten in 2008, and then some work by Asel Kashikawa and collaborators in 2022. So they have some criteria such that this theory actually. This 3D n equals to 3 Chern-Simons method theory enhances to 3D n equals to 4 if they satisfy the following criteria. First is the moment map. The moment map for each flavor symmetry satisfy the following constraint. Sorry, can you see it?
Yeah.
That is basically the trace mu squared is equal for every moment map. Actually, this type of constraint appear in many cases. For example, if you're familiar with TN series, these are one of the moment constraints that moment map has to satisfy. Of course, for the bifundamentals, you can compute directly that this moment map satisfy automatically. And the second criteria is a criteria on the Chern-Simons level. That the sum of the inverse of Chern-Simons level has to be 0. So once these two conditions are satisfied, the resulting theory will enhance to 3D n equals 4.
Sorry, what's the meaning of the first condition given that these are functions, not just numbers?
Sorry, you mean
So,
this one?
right, so moment map is a function, right? The trace of the square of that is also a function.
Yeah. So this is the same as function.
Same as functions?
Yeah. Right. For example, that for this one, you can build the moment map directly, right?
Right, so for
As
them to
a
be...
Q and Q tilde.
Yes, so they are function on like the same vector space, you are saying?
Yeah. So for example, for this, if you call in the n equals 2 language, you call this I and J. sorry, I and alpha, where I is the index of this and alpha is indexes of this. And the other one is Q tilde I and sorry, J and beta. And then the moment map mu1 as is roughly I alpha, Q alpha Q tilde J alpha, right? Sum over alpha. Yeah, and the moment map mu1, mu2 is roughly, sorry. And you compute the okay, yeah, I think I didn't write it. I think I write it correct. And then you can do a direct computation to verify the concept.
Yeah, I see.
Okay. Any further questions? Okay, let me first explain the mechanism behind this SUSY extension. So this explanation was due to ATT paper, and I found it very nice. So this let me explain this mechanism. So first we start with N equals 3 Chern-Simons map. And there is a superpotential proportional, right this way. Trace phi I ui minus ki over 2 trace phi I squared. Where this phi I is the adjoint scalar of the three vector multiplier. Okay. And this is of course moment map. So we see that when this term, when ki equals to 0, so we don't have the last term coming from Chern-Simons term, then actually there is a U1 action acting on this, which the superpotential is invariant under. So and this phi has a +2 of this U1 and -2. Mu has -2 under this U1. So this U1 actually, I've skipped some details, but this U1, roughly the U1 is one of the U1s in the SO4R. So because of this existence of such U1, the theory actually enhances from 3D equals 3 to 3D equals 4. However, as you can see that when this Chern-Simons level is non-zero, this U1, the W is not invariant under this U1. So that's why in general you have only 3D equals 3. However, okay, when k not equals to 0, but because notice that in our construction, we only introduce Chern-Simons term. We don't introduce any kinetic term for the vector multiplet. So when k not equal to 0, one can still integrate out, because there's no kinetic term for this adjoint scalar. So one can integrate it out. So integrated out phi is the superpotential proportional to sum over I 1 over ki trace mu I squared. Okay. Then you see that if the superpotential after you integrate it out, if this thing is 0, there's of course because this is 0, then of course it's the origin of broken U1 symmetry actually automatically becomes a symmetry of the superpotential, which is 0, right? So this U1 symmetry was restored. So so in the IR, we found that the supersymmetry enhances from n equals 3 to n equals 4.
Okay.
Yes?
There is a moment map for each node, gate node, right?
Yeah.
And there's further mu1 and mu2. What are they?
What do you mean by that?
So the equation on the right is trace mu1 square equal trace mu2 square equal trace mu I squared, right?
Yeah. So if I have a
Gauge.
if I have like a two flavor group,
Oh,
I
you-
have only mu1 and mu2. But if I have some more complicated case like Tn series, this Tn series actually have a three flavor group: SUN1, SUN2, SUN3, right? So in principle, for each flavor group, you have mu1, mu2. You have a mu1 and then mu2 and mu3. So as you can see, that the simplest set of solution for this thing equal to 0 is given by this condition. So that's why once we have this balancing condition, the superpotential it becomes 0.
But there are other solutions, right?
Yes, it's possible, but in that case, it's probably not very easy to study systematically.
But like for Tn theory, are there other solutions?
For Tn theory,
Or even by fundamentals? So probably you want to show that.
okay, so for I guess for example for bifundamentals, okay, yeah, let's see. So for bifundamentals, let's see, for bifundamentals, we say it's already we have trace mu1 squared equal to trace mu2 squared. Then in that case, this superpotential after integration is k1 plus k2 trace mu1 squared. So indeed, I mean, because we already had this constraint, so indeed in that case, you have only one solution.
But we choose different representations, right? So something else that has a map to UN.
But
Like I choose the other guy to be just a U1. I just get the U1 part of the UN one.
yeah.
And then I change the level to something else. So would that obviously won't work?
No, this is not the U1 part of it. No, this is not.
I mean, for the left node, I just gauge the U1 part of the UN, right? So that's also fine. But maybe that obviously won't work for some reason.
That's why you need just a gauge U1 K and here UN minus
Right, right, yeah.
something K2.
Some level.
Okay, first I don't think that you have the nice constraint on the nice relation on the moment map in this case, but then you have to be careful. I'm not sure. I don't know whether this is this can still it can still possible.
So maybe they are proportional because this measuring norm square on this
Yeah.
space.
So.
But I'm not sure.
Okay, I guess you. In that case, if you write down this as equation functions, you may find that they may be W as a functions of Q, they may vanish at certain value of Q, but you probably cannot find the W vanish for every value of Q.
Might be
That's,
possible.
much better.
And just make sure, so for this U1, so you will not commute with the SO3 R symmetry of the Hugo 3 theory.
Oh no.
Is that obvious?
I guess it's let's see. So this U1 you can build this as a global symmetry such that yeah, I don't have an alternate counter, but we can see it. But I had a feeling that since these two things have different in one chart, that it's probably some rotating this to them. But of course, that's not a precise argument. Yeah, thanks for the question. Yeah. Yeah, I don't have the precise argument out of my paper. Yeah. Okay. So this is Tn's bifundamental, and the other idea is Tn theory. So if I call this node SUN1, this SUN2, and this SUN3, there is a famous constraint that the moment map trace moment map square for all these three, they has to be the same. They satisfy this relation. This can be read from for example, you can read this from the superconformal index. And also you can actually show that by looking at the Coulomb branch of the 3D mirror field. Okay, and you see that now this superpotential term is proportional to sum over ki and trace mu1 square. So again, if the level in this case, if the level satisfies this balancing condition equal to 0, we restore equal to 4. So actually, there are more series. So suppose. So look. I mean, for all these things, I actually started with some 4D equal 2 series with flavor symmetry and such condition constraints on the moment map, and then compactified on 3D to get a 3D equals to 4 matrix series, and then couple. So actually, you can also start it with the Argyros-Douglas method. Which I will not talk in detail, but there are some Argyros-Douglas matter series with flavor symmetry G1 times G2. And you can also show from index that for such Argyros-Douglas matter series, they also have trace mu1 square, trace mu2 square. This also have this constraint. So this Argyros-Douglas matter series is a vast many field of Argyros-Douglas matter series, which can be viewed as a generalization of or some non-Lagrangian generalization of bifundamentals. So from that you can build a lot of more Chern-Simons 3D equals 4 Chern-Simons matter series.
So these are dimensional reduction of the 4D theory with the same name, or?
Yes. So when I write down this series, I just started with the 4D equal 2 series of this type, and doing the naive circle compactification on the 3D, and I supposed to get the 3D equals 4 series, which are Okay, so there are some further generalizations to this thing. So you can actually have more complicated. So it's like a GUI. Say for example, you can start with bifundamental N1, N2, right? And another set of bifundamental N2 and N3. Okay? And we have let's take the diagonal action of this UN2 and UN2 here, and gauge the diagonal flavor group with Chern-Simons term. Eventually, I will get something like this. So described by the flavor like this, it's some N1, N1 Chern-Simons term, and N2 UN2 Chern-Simons term, and UN3 Chern-Simons term. Okay. And now the moment map constraint is trace mu1 square equal to trace mu1 square. Mu2 1 square. So this mu2 1 square are the moment map that build from the left one. And then the other one is trace mu2 2 square. These are the moment map built from the, so I will call this Q1, Q1 tilde, and Q2, Q2 tilde. And this is a moment map trace mu3 square. Okay. Then in this setup, after integration, so we start with this superpotential K1. Sorry, this is a Ki sum over I trace phi I square. And then we have the K1 trace phi 1 mu 1 and plus trace phi 3 mu 3. So this 1 and 3 are the same as before. However, for the 2, it's actually trace phi 2 because it's coupled with both the moment map coming from this hyper and the moment map from this hyper. So it's mu 1 1 and plus mu 2 1 and mu 2 2. Okay. Then after integration, so after integration and impose the constraint, we get K1 plus K2 trace mu 1 square and mu 2 plus K3 trace mu 3 square. However, there are like crossing terms between mu 2 1 and mu 2 2. So there is an extra term 2 over K2 trace mu 2 1 times mu 2. Okay. So apparently to let this superpotential to be 0, so this superpotential can never be 0 if you have a non-zero Chern-Simons level. But you can choose the balancing level like K minus K and then K, so that this term becomes 0 and this term becomes 0. But you're still left with the following crossing terms, right? But how do you make it invariant under the U1? You actually can choose that this mu2, the first one has charge under +2, and the second one charge under -2. So how is that possible? That basically means in this case, so you see that this flavor, this SU2H and SU2C are just a matter of perspective. So whether you call it Coulomb branch SU2 or Higgs branch SU2, it's just you have the ambiguity of defining this. So in this case, here, if I choose this to be hypermodulate, I have to put this to be something called twisted hypermodulate. So basically, a twisted hypermodulate is basically the same as a hypermodulate, but with the SU2C and SU2H charge, like interchange. So once I choose the hyper and twisted hyper, I automatically have this U2, the first one, the moment map for the first one is charged under plus 2, and the moment map of second one charge on the minus 2. So although in this case the superpotential is not 0, it's still invariant under this U1. So so in the case it gets enhanced. Of course, I mean similarly I can continue. So again, to make the superpotential invariant under U1, I have to use hyper here, some N4 and minus K, and continue on forever. So that actually this is a way of how you sort of gluing it to a more complicated Chern-Simons matrix. You can also do it for the T3 series. So suppose you have you can also have Tn series. You have a Tn series. You sort of gauge it. K1, K2, K3. But again, the computations are similar, and to make the final superpotential invariant under this extra U1, so you have to choose this the other Tn series with some reverse charge. So it's some twisted version of Tn series, which you can actually always do. So you for the Tn series, because it has 3 legs, you can even have more complicated legs to gluing. You can, for example, you can have you can have 4 set of different pieces of Tn series that 2 of them are like interlocked with each other and more complicated. Right? Of course, you can also do it for the Argyll-Stockdale matter and compute it. Okay.
So just I think you're going to mention, but does it have? So you don't turn on the Yamez term?
No.
Right?
It's crucial.
Yeah,
that I don't turn on.
Yeah. Is it? Does it have an interesting Coulomb branch? I think you're going to mention it.
Good question. Thank you. So I'm going to mention that, but so let me tell you let me just spoil. So for this one. No, you don't have a Coulomb branch because I can compute the Coulomb branch index is actually 1, so it's not interesting, right? It only has fixed.
Yeah, that's what I thought.
But however, if you start with this one,
Yeah.
hyper, twisted hyper. So let's, for simplicity, let me just put it everything together. You actually have a Coulomb branch. Because now this twisted hyper, their charge are reversed. So the SU2C actually acts on non-trivial.
Yes.
So this series actually has both fixed branch and Coulomb branch.
Yes.
Moreover, you can see this series is completely symmetric when you exchange SU2H and SU2C. Right? So you exchange the hyper and twisted hyper, it's the same series. So this is actually a self-mirror.
Okay, so the Coulomb branch parameters are this Q2 and the Q2 tilde. Babel.
Yeah.
I see.
Well, I mean, actually, the Coulomb branch operators are more complicated.
Oh, I see.
Yeah. So, but classically, you can view this Coulomb branch roughly.
For that Coulomb branch, is it a single hyperkiller cone? Because the Coulomb branch looks bad without any layers.
You will see. That, yeah. So this is a way of actually constructing self-mirror series.
Didn't it show that now you look like a subspace of the mixed branch as opposed to being a
Yeah, I haven't discussed anything about mixed branches. It's too complicated for that's why. Yeah. In that sense, I mean, supersymmetric index is not that useful. Okay, so yeah. I have remaining 20 minutes, so let's go into study the moduli spaces of the series. I mean, by moduli spaces, I mainly mean the Higgs branch and the Coulomb branch of this thing. Sorry, so far no Higgs branch. honest, I didn't really. Because I'm computing index. So what I'm really count is the graded dimension of the function ring on the Higgs branch and the Coulomb branch.
So Hilbert series.
Right?
Hilbert series.
Yes.
Okay.
And so for this, so this ring are generated by the Higgs, so-called Higgs branch operators. So this is Higgs. I will call it Higgs ops, and these are generated by the Coulomb branch ops. So index can help us counting this such ops, and these operators satisfy the following BPS condition. So this delta is the conformal dimension, and RH and RC are the cotons of SU2H and SU2CR symmetry, and J3 are just the spin of the 3 dimension. So these are the usual BPS condition has to satisfy, and Higgs branch has to satisfy an extra condition that the delta equals to the RH. And Coulomb, it's similar, so it has a similar constraint. But here you have to change. Okay. So to count these BPS operators, I actually let me write it this way. Right in here. Yeah, actually, you shouldn't ask me that question because I already told you what modulus this that I got last year. Yeah, the index is a trace over the Hilbert space satisfy this BPS condition. And with the -1, QJ3, Q delta minus RC, and Q delta minus RH. And it also possibly depends on the fugacities of flavor, actual flavor symmetry. But in our case, I gauge every flavor symmetry, so we don't have this part. Okay. Well, but there may be some topological U1 that come. So from the so this Hilbert space is I sum over all the Hilbert space satisfy this BPS condition. So apparently that the Higgs and the Coulomb operators are counted in the index. Then if I wanna single out all the Higgs branch operators, which satisfy delta minus RH equal to 0, I can send this Q tilde. So Higgs is sending Q tilde to 0. We'll keep this Q finite. Right? And if I want to say all the Coulomb branch operators, I send Q to 0 and keep Q tilde fixed. So this is a strategy of reading out the Coulomb branch spectrum and Higgs branch spectrum. It just for a given series, since it's Lagrangian, you compute the index, and then you take the limit. Okay, sounds simple, right? But there is a caveat. In 3D, we have the contribution from monopole operator. These monopole operators complicate things a lot, especially in the 3D Lucas flow case. So for a monopole operators, I mean for each gate group, we have a monopole operator. We can have a monopole operator labeled by Vn, and this M is some monopole charge which are in the co-weight lattice. Co-weight lattice of the gate group G. Okay. And And it's an important fact that let A be the connection of a gauge symmetry, or let A be some background connection of a flavor symmetry. In that case, then it's possible that this monopole are charged under this symmetry with whose connection is A, right? The particular charge of the monopole operator is actually determined by the formula. So this level is the Chern-Simons level between A symmetry and the gauge symmetry, gauge connection, AJ. Okay. So once you have some Chern-Simons level between this A and your gauge group, to define the monopole operator, you are possibly have some. Your monopole are possibly charged under that symmetry. Right? Another contribution. This is from this coming from one loop correction of fermions. Okay. So once you have a fermion which is charged under this gauge group, then the monopole charge under this A are corrected by the fermions, if these fermions are also charged under this symmetry. Okay. So this is a moreover, this once we have a monopole operator, we can also dress this monopole operator with some other operators. As long as these operators are massless, or they have they are effectively massless under the monopole background, right? So because if you didn't change the mass, and you can dress the monopole operator with this, and you basically didn't you didn't break the BPS condition, right? And so suppose X is a matter field. You actually the effective mass under the of X under the monopole charge is this. So it's the representation of X acting on the M. Okay. So this monopole operators, we have a bunch of dressed monopole operators that may also contribute to our index. So in the end, what we are counting is the gauge invariant monopole operators dressed with massless terms. Okay. But luckily, actually, the formula for the to compute the index, all these corrections are automatically included. Which is so usually when you compute the index, you have it. This 3D index, you sum over all the monopole charges, and you divide it by the order while group of the remaining gauge group, and you integrate over all the gauge group. And you have different the Chern-Simons, vector, and hyper contribution. But you remember that for each contribution, there is some contribution which in literature called zero-point energy. Which exactly keeps track of the correction of the charges of monopole under all these corrections.
So here M are just the fluxes of the for the cartan over the S2, right?
Yes, yes,
Yes.
yes.
So okay, and they just happen to have the same label as multiple operators.
No. This M here
Right.
are exactly this the multiple charges.
But here in interpretation in terms of index is that these are fluxes of the
They are
U1.
just the same.
Okay.
Okay, so right, my time is out. Let me give you some results. Yeah, so let's start with this example discussed already by Jeffers in 2008. It's a U1 K minus K. You can compute its Coulomb branch index gives you 1. That means the Coulomb branch is some points, so it's trivial. But Higgs branch index, so once you compute the index, you take the limit, which is Q that goes to 0 limit. And it's actually this one. So from the index itself, you see that it's quite possible, because this has the same Hilbert series as C2 mod ZK. So it's quite possible that in this case, the modular space is C2 mod ZK, which described by the UV plus ZK equal to 0. Right. Okay, that's a simplest example, and actually. Although the full supersymmetric index cannot compute in a closed form, but this one, this Higgs branch limit can be shown that it is this expression precisely. Okay, now answer your question. Right. For example, so now once I have a hyper and twisted hyper, right? It's actually a bit funny. So this is a self-mirror case. Actually, the Higgs branch and the Coulomb branch, from the index, it should be C2 mod ZK plus 1. Or you have to be careful, there's a plus 1 here. So somehow adding this twisted hyper change both the Higgs branch and Coulomb branch. That is because basically because of here. The charge of the monopole operators get changed. So you already see that in the previous case that even so usually in without Chern-Simons level in the 3D n equals to 4 case, monopole operators didn't contribute to Higgs branch. That is a fact. Monopole operator usually contributes only to the Coulomb branch. However, in the previous example, you see because of Chern-Simons level and shift of the charges, monopole operators now may contribute to Higgs branch in the Chern-Simons matrix series. Okay.
So in this example, without the Chern-Simons level, I would have a 2 quaternionic dimension object. But now with the Chern-Simons level, it's only becoming 1 quaternionic for the Coulomb branch.
Yeah.
So in this case, in what sense it contributes? So the dimension will not change for the Higgs branch, right? So sorry, the
Yeah, the classical dimension didn't change, but the relation changed.
Okay.
Yeah. I will give you a more complicated example. Yeah, that also answers your question. So let's for non-abelian case. For simplicity, let me start with un and k level minus k. Right? And to have a good theory, I have to have the constraint that k greater or equal to 2n minus 1. So this k has to be large enough. So in this case, the Coulomb branch index is still 1. The fixed branch index is actually it is a complete intersection from the Hilbert series. Right? You see, it's a rational function of 1 minus something. And in this case, the classical fixed branch, I mean, roughly it's a unsymmetric copy of this one, right? So the classical fixed branch is the symmetric nth power of C2 mod Zk. However, this is not a complete intersection. But from the index computation, this looks like a complete intersection. So what are the actual quantum fixed branch? It actually troubled me a long time to find what are these things. So it's okay. Let me just say the Hilbert series of the Higgs branch is the same as the Hilbert series of Sudol slice labeled by this Newport orbit Newport orbit labeled by this partition intersect with the Newport cone. This is a Newport cone of new cone of SUK. So this is well, okay. To be precise, that this is some result coming from reading the index. Okay, but right now, so far, I guess it's not proven, but it's very likely that if the Hilbert series matches, it's pretty sure that the modular space of Higgs branch should be described by this. So, but this is actually very interesting. That means the modular space, the Higgs branch of this theory, of this Chern-Simons matter theory, is the same as the Coulomb branch of non-Chern-Simons theory. However, this is not a 3D mirror because the Higgs branch of this thing is non-trivial, while the Coulomb branch of this is one. So I still don't understand how this quantum correction of this thing, this classical modular space, actually gives you the intersection of Sudol slice with a new cone. But this seems to be the result from reading the operator. Okay. Sorry, my time is really up. Also, you see, you can build self-mirror cases from this. It's roughly that in this case you will have a self-mirror theory where both of the Higgs branch and Coulomb branch are some complete intersection. So it's similar to this case it only modifies slightly the structure like this ZK here. Effectively, if it only modifies the effective Chern-Simons level, but roughly the moduli space are roughly in the same category. So this is an example of 3D Chern-Simons series that both Higgs branch and Coulomb branch are intersection of Simodoid slice, which is actually quite different from the usual quiver gauge theory. Because usual quiver gauge theory, on the one side you have Simodoid slice, on the other hand you have like a closure of the important object. Okay, so sorry. The last example is really like the T2 series. So again, the Coulomb branch is trivial, but the Higgs branch moduli space of this thing is described by the D-type singularity C2 mode K-hat with some number D here depends on K1, K2, K3. So again, we see a situation that even for the Chern-Simons matter theory, its quantum Higgs branch is something that we saw before. That has a quiver distribution. So, however, it's still very mysterious to me why somehow the Higgs branch of this thing is the same as Coulomb branch of some quiver gauge theory, but it's not mirrored. Okay. So my time is up, so I think that it's good to end here. Of course, there are a lot of dualities which can be checked by this index. So I will mention one last example. It's about duality. That is really a mirror. So we check that the supersymmetric full index are indeed the same on the exchange. So, but this reverse a function u1 with level 1 and u1 level -1. So the total number of gauge nodes are 2R, and these are mirrored to the following non-Chern-Simons matter theory. So this Chern-Simons matter series are mirrored to this following normal n equals 3D n equals 4 gauge series. Okay, so mirror. This can be checked by the combination of three indices, and this can also be checked by Bruin argument. Okay, so I guess I will end here. Thank you.
Question?
So, do you know any Greenwald construction restricted hyper cases which you can realize, you can easily realize this R symmetry geometry?
Good question. So let me say, for example, in this case, there's a standard brane canonic Witten type construction that you have roughly one brane. Yeah, if I remember correctly, this you have a bunch of one branes, and you have these three branes between them. And basically, you can see that then you will have a hyper and twisted hyper and Chern-Simons level.
So maybe alternating 1, 1, 1, 0.
Yeah. Sorry, you're right. Yeah. So 1, 1 and NS5. and then 1 1 and then 5. Yes. Yeah, then you will see that the Chern-Simons here is 1 minus 1, 1 minus 1, and then automatically you have hypers and implicit. But in general it's in general it should be like you have 1 K brain and NS5, and then 1 K brain and NS5. And you may have a bunch of D3s, different number of D3s. That basically gives you the Hanani-Witten type of construction of this type of thing. Yeah, but okay, how to generalize it to bring web? I'm not familiar with it. I guess you guys are experts on that. Yeah, actually, this is also a good question, because from this picture, I can do a S duality to change this 1 1 brain to D5 brain. So eventually, this is possible. So this is after some S and T dualities. That's because I have 1 1 here. If I have so that's why I can mirror this Chern-Simons matrix theory with level 1 minus 1 to non-Chern-Simons level 3 equals 4 0. However, if I have a general Chern-Simons level 1K here, I cannot find a S and T chain of S and T dualities to make it non-Chern-Simons level. So okay, maybe because I'm not good enough on this, maybe I need the input from expert that whether there can be chain of dualities starting from this configuration and eventually getting some non-Chern-Simons description. That will be more interesting, right? Yeah, to have a duality, and that may also understand why this thing works. Okay, yeah.
Maybe a naive question, but related. But can you construct any of these theories with these 5 brains wrapping 3 manifolds?
Yeah, that's also a good question. I don't know.
I see. So in principle, it's not discarded immediately.
Yeah, it's not
This
discussed.
looks possible. TN with Chern-Simons.
Yeah,
I think so.
yeah.
But I don't know this quiver. Any other questions?
So from the S duality of that brain setup, how do you get the 2 flavors in the mirror? Because you do it to get 1 defined brain, right? Or shouldn't there be another one?
Looks to me, yes.
Oh, well,
Maybe there's some Hanani-Witten moves there.
yeah, you first deal to this, and then you to get a mirror you have to flip, and then you do Hanani-Witten mirror. Come on, you are from Hanani school. You should figure out this.
Any other question? If not, let's thank the Wenbin.